And if you have ever cooked over a wood fire, you know the ritual. The flames are lively, the heat is radiant, but the aftermath is a stubborn, greasy film that coats every surface. Pots blacken, chimneys clog with creosote. The campfire leaves behind a residue that demands scrubbing, scraping, and chemical solvents to remove. Now consider a modern gas range, a blue ring of flame that ignites cleanly, burns completely, and leaves the cooktop virtually spotless after years of daily use. The difference between the two is not merely a matter of convenience, it is a matter of molecular destiny. A wood fire burns a complex stew of hydrocarbons, tars, and volatile organics that never fully decompose in the flame. A methane flame burns a single, simple molecule, CH4, that, given sufficient oxygen and mixing, vanishes into carbon dioxide and water vapor with nothing left behind. And this domestic contrast translates directly into the life and death economics of rocket engine reusability. For decades, the workhorse fuels of orbital rocketry were kerosenes, RP-1 in the west, RG-1 in the east, refined to remove the heaviest aromatics but still fundamentally a mixture of long-chain hydrocarbons. In a rocket engine, these fuels do not merely burn, they pass through a punishing thermal gauntlet before they ever reach the combustion chamber. In a regeneratively cooled engine, the fuel is routed through hundreds of narrow channels milled into the copper or nickel alloy walls of the combustion chamber and nozzle. It serves as a coolant, absorbing the searing heat that would otherwise melt the structure before being injected into the flame. This clever arrangement, described earlier in the context of the Raptor's regenerative cooling, works brilliantly so long as the coolant remains a clean fluid. With kerosene, it does not. In the chemistry of clogging, why kerosene leaves a trace at elevated temperatures, the long hydrocarbon chains of kerosene begin to crack. Thermal cracking is a familiar concept from petroleum refining. Heat breaks carbon-carbon bonds, producing smaller fragments. Some of those fragments are lighter, more volatile molecules that remain dissolved or gaseous. Others, however, are carbon-rich solids, amorphous carbon, graphitic platelets, and sticky polycyclic aromatic hydrocarbons that agglomerate into a substance known as coke. Coking is the bane of any heat exchanger that uses a hydrocarbon fluid. Inside the cooling channels of a kerosene-burning engine, a thin, progressively thickening layer of carbonaceous gunk deposits on the walls. This layer acts as an insulator, reducing the heat transfer from the hot gas side to the fuel. The wall temperature rises, accelerating further coking in a vicious spiral. The deposits can partially obstruct the channels, raising the pressure drop and starving the injector of fuel flow. In extreme cases, chunks of coke can break loose and clog the injector orifices, causing combustion instability or catastrophic hot spots. And for an expendable engine, coking is a manageable nuisance. The engine only needs to survive a single firing lasting a few minutes, and the design margins can accommodate a certain amount of deposit buildup. For a reusable engine, coking is a deal breaker. After each flight, the cooling channels would contain a stubborn residue that cannot be flushed out with solvents without disassembling the engine. The idea of tearing down a complex turbomachinery assembly to mechanically clean hundreds of narrow passages after every mission is absurd from an operational standpoint. It would make airline-like reusability impossible. The engine would need a ground crew of specialized technicians and a multi-day turnaround, destroying the economic case for rapid reflight. This is why, when SpaceX set out to build an engine that could fly multiple times with minimal inspection and no major refurbishment, kerosene was never a serious contender for the Raptor. The fuel had to be inherently clean-burning, leaving no residue behind even after repeated thermal cycling. And methane's molecular simplicity. Methane's chemical simplicity is the source of its cleanliness. The molecule consists of a single carbon atom bonded to 4 hydrogen atoms, arranged in a tetrahedron. There are no carbon-carbon bonds to crack, no long chains to fragment into heavy residues. When heated to the temperatures found in a regenerative cooling jacket, typically several hundred degrees Celsius, methane remains stable. It does not polymerize, it does not form polycyclic aromatics, and it does not deposit solid carbon on metal surfaces. Even if some thermal decomposition were to occur at extreme hot spots, the only possible solid product would be elemental carbon, but the reaction kinetics are so unfavorable at the operating conditions that no measurable coking occurs. The methane molecule simply refuses to leave a mess. And this property has been validated in thousands of hours of testing at SpaceX's McGregor facility and in the flights of the Raptor 2 and Raptor 3 engines. After a full-duration static fire, inspection of the engine's internal passages reveals surfaces that are essentially as clean as when they were machined. There is no carbon buildup, no sticky film, no need for solvent flushing. The engine can be fired again within hours, not weeks. This cleanliness is not a minor convenience. It is the enabling characteristic that transforms a rocket engine from a precision instrument requiring constant pampering into a robust piece of industrial equipment capable of hundreds of missions with only periodic inspections. The Raptor 3 design goal of 1,000 flights per engine without major overhaul rests squarely on methane's refusal to foul its own plumbing. and a cleaner API for propulsion. For the computer scientist or systems architect, methane's behavior can be understood through the lens of a well-designed application programming interface. A good API does one thing, does it predictably, and produces no unexpected side effects. A bad API leaks memory, mutates global state, and forces the developer to write endless cleanup routines. By this measure, RP1 kerosene is a legacy API with hidden dependencies and undocumented failure modes. Its thermodynamic properties vary from batch to batch. Its viscosity changes sharply with temperature. Its tendency to coke depends on trace impurities and the thermal history of the fluid. Methane, in contrast, is a clean, stateless function, given a temperature and pressure. Its properties are known with high fidelity, and its output is always CO2 and H2O with no leftover side effects. It does not leave a residue in the pipes, does not react with the metal walls, and does not change its chemical identity during its passage through the engine's circulatory system. And this predictability extends to the design process itself. Engineers modeling the regenerative cooling network can rely on methane's well-characterized heat transfer coefficients and phase behavior without having to account for time-dependent fouling factors. The turbopump seals can be designed for a fluid that will not varnish or gum up the running clearances. The injector can be optimized for a single, well-defined combustion chemistry rather than a variable mixture of hydrocarbons. In essence, methane reduces the number of unknowns in the already formidable equation of a full-flow staged combustion engine. It is a fuel that behaves like a well-documented library, not a tangle of spaghetti code. For an organization like SpaceX, where rapid iteration and simulation-driven development are core to the engineering culture, this reduction in cognitive and computational overhead is a force multiplier. In the common bulkhead, cryogenic sympathy methane's virtues extend beyond chemical cleanliness to a thermal coincidence that simplifies the entire vehicle architecture. Liquid methane at its normal boiling point is a cryogen, though not as frigid as liquid oxygen. At 1 atmosphere, methane boils at approximately 111.6 Kelvin, compared to oxygen's 90.2 Kelvin. However, SpaceX subcools both propellants to pack more mass into the tanks. The LOX is chilled to around 66 Kelvin, while the methane is typically subcooled to somewhere near its freezing point of 90.7 Kelvin, often in the range of 90 to 95 Kelvin. This means the two liquids, while not at identical temperatures, occupy a similar cryogenic neighborhood. The temperature difference between the LOX and methane tanks is manageable enough that they can share a common bulkhead without one fluid freezing the other solid. And in the Starship and Super Heavy vehicles, the propellant tanks are stacked vertically, separated by a dome-shaped bulkhead that serves as the floor of the upper tank and the ceiling of the lower one. If the two liquids had widely divergent temperatures, the warmer fluid would constantly heat the colder one, driving boil off, or the colder fluid would freeze the warmer one into an unusable slush. With kerosene and liquid oxygen, this is a genuine problem. RP1 is stored at ambient temperatures, while LOX sits at cryogenic temperatures. Their tanks must be thermally isolated, typically with an interstitial compartment or a heavily insulated common dome that adds weight and complexity. Methane and oxygen, by virtue of their cryogenic sympathy, can share a single, relatively thin bulkhead without elaborate insulation. The thermal gradient across the dome is modest, and the heat flux is manageable with the vehicle's normal boil-off management. This design simplification saves hundreds of kilograms of dry mass and eliminates potential failure points, a perfect example of how a fuel choice propagates benefits through the entire system. And the soft benefits of a gentle fuel. Methane's benign nature manifests in other, less obvious ways that collectively lower the barrier to reusability. It is non-toxic and non-carcinogenic, unlike hydrazine derivatives used in many spacecraft thrusters. A methane leak, while a flammability hazard, does not require the hazmat protocols that a leak of hypergolic propellants would demand. Ground crews can work around methane systems with standard combustible gas monitors rather than full protective suits. Methane is also a gas at ambient conditions, which means that after engine shutdown, any residual liquid in the plumbing simply evaporates and vents away, leaving no puddles of corrosive or toxic liquid to deal with. This self-purging behavior is another facet of the no-cleanup philosophy. The engine, after emission, returns to a dry, inert state with minimal intervention. And furthermore, methane's gaseous nature at room temperature makes it easy to pressurize the fuel tank using autogenous pressurization. The Raptor engine taps off a small stream of gaseous methane from the regenerative cooling circuit or from a heat exchanger to maintain the ullage pressure in the methane tank, eliminating the need for a separate pressurant like helium. This is possible because methane can be vaporized and superheated without decomposing. The same cannot be said for kerosene, which would coke inside a heat exchanger if one attempted to vaporize it for pressurization. Autogenous pressurization reduces the number of consumables the vehicle must carry and simplifies the fluid schematic, again a direct consequence of methane's chemical stability. And the Martian key. All of these terrestrial advantages, cleanliness, cryogenic compatibility, operational simplicity, would be sufficient to make methane an attractive fuel for a reusable launch vehicle. But for SpaceX, the choice was never only about Earth. The company's founding purpose is to make humanity a multiplanetary species, and Mars is the immediate destination. On Mars, the atmosphere is 95% carbon dioxide. The polar caps and subsurface regolith contain vast quantities of water ice. With these two resources, a simple chemical pathway can produce methane and oxygen in the exact ratio needed by the Raptor engine. The Sabatier reaction, combined with water electrolysis, takes Martian CO2 and H2O and outputs CH4 and O2. No exotic mining, no shipment of fuel from Earth, no dependence on a fragile supply chain across millions of kilometers of interplanetary space. The propellant that powers the return journey can be manufactured on the surface of Mars using nothing more than local materials and a power source. And this is the ultimate expression of methane's clean nature. It is not only physically clean in the engine, but logistically clean in the mission architecture. A rocket that burns methane can be refueled at its destination, with a process that is chemically straightforward and scalable. The Raptor 3, with its full-flow staged combustion cycle optimized for methane-oxygen combustion, becomes the bridge between the launch pads of Earth and the dusty plains of Mars. The fuel that keeps the engine pristine after 100 flights is the same fuel that will one day be synthesized in a pressurized dome on another world, using the thin Martian air and water extracted from frozen soil. The clean-burning Martian key is not a poetic metaphor. It is a deliberate engineering choice that aligns the engine's operational behavior on Earth with the resource constraints of an interplanetary civilization. And this brings us to the next critical piece of the interplanetary puzzle. 2.4 The Sabatier process, refueling on the red planet.